There we go. Hello and welcome back to Statistics 1. This is the last lecture of Chapter 5 on binomial distribution. Now, before we dive into binomial distribution, we have to deal with some mathematical notation, right? It's just like learning a foreign language. You have to know the words first, and then you can form sentences that communicate. So, what do? First, we learn about factorials. So, factorial. And you will see this notation. This is read as n factorial. This is not n, it's n factorial. So, cool off when you see it. And the meaning of it is you multiply all of the numbers, integers, starting at 1, all the way up to whatever that n is. So there will be n minus 1, and then finally the last one in the sequence would be n. So you multiply them all, and generally this gets to be a very, 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 very large number very quickly. So 1 factorial, well, let's start with a 0 factorial. 0 factorial is defined to be 1, and then 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, 24. 5 factorial is equal to, lazy to write all of this out, 120, going on to whatever amount you need. Now, a very useful formula is to understand that n factorial can also be written as n times n minus 1 factorial. This is a useful formula, and you don't have to break it at 1, you can break it at any other value as well, which is actually what we're going to use. To give you an example, 6 factorial is equal to 6 times 5 factorial. And that should make sense because all of the numbers 1 through 5 are under 5 factorial, and then times 6. That makes it 1 through 6, and that's 6 factorial. So that's just an example. But you can peel more than one term only. Let's say you can also go with a 6 factorial and write it as a 6 times 5 times 4 times 3 factorial. Because maybe you need to cancel 3 factorial, so you just peel off all of the other terms. So this would be 120 times 3 factorial, right, for the 6 factorial. So this is just introduction. So factorial is simply going to multiply all of the integer numbers 1 through n, n being the last one. So the value of the factorial right here always matches the highest integer you are multiplying, and you have to multiply all of the integers starting at 1 all the way to that n. And then the formula where you can, what I say, peel off a certain amount of numbers depending on how many you need. We'll see where we need that in application and move on. Yes?
How does 0 factorial equal 1?
It's by definition. It's by definition. There are some mathematical proofs out there. We said just put definition. As you can see, none of these products here have 0 in it. Now, the next one, the next definition that we need to survive this is binomial coefficients. And binomial coefficients are denoted almost as a fraction. There is no line. It's not a fraction. It's about notation for binomial coefficients. And the formula to compute this monstrosity is this one. So these would be your binomial coefficients. Now we'll see where all this falls in a place. Now, to calculate these binomial coefficients, you will just crank this formula. So let's say you have 2 choose 6. Well, you know that your n is 2 and your x is 6. You just plug them in where they belong. It's a 2 factorial divided by 6 factorial times 6 minus 2 factorial, which is 2 factorial divided by 6 factorial times 4 factorial. Oh, I got it completely reversed. 6 choose 2. Much better. There we go. 6 choose 2. That's the way you would read it. 6 choose 2. So now, to use the formula that I have over here in this blue square, in a blue box, I'm going to peel 6, I'm going to peel 5, and I'm going to leave 4 factorial on a pile. 2 factorial is 2 times 4 factorial. Now 4 factorial cancels. And what I'm left with is, I can cancel 6 and a 2, and the answer is 15. So now I have 6 times 5 over 2, which is equal to 15.
How do you get a 4 factorial?
Using this. We peel off integers. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And the 4 factorial is this, so I'm not going to expand it, I'm just going to leave it. So 6 times 5 times 4 factorial. So you just peel off what you don't need, and the rest of it's in the factorial stays, and you just cancel the whole thing. It's very helpful for large numbers. I think that the largest number that you can do as a factorial in your TI-83 calculator, 84, is either, I think it's 70, it might be 69, but I think it's 70. The largest number that calculator can compute. Factorials tend to be extremely large numbers very quickly. Those of you that use TI-83, 84, you can find factorial under math button, which is under alpha key, which is under second key. So let me just see.
Is that like you use Android?
You keep poking, man. You keep poking. You keep poking because you know I highly hate and disrespect Apple as a company. And then you keep poking and you keep poking. It's not gonna change. Yep, 70. So 69 is the largest factorial you can calculate on TI-83, 84, and then 70 gives the overflow in memory. That's only one of the aspects why.
Okay.
There is much more moral and ethical considerations. So yeah. Anyway, so these are the calculations. Now let's take a look at one more. This one is going to have considerably larger numbers. So let's say you have 28 choose 9, for instance. Calculating something like this in a calculator would be absolutely crazy. So you have to do what we call peeling, right? On top you have 28 factorial, the bottom you have 9 factorial, and then 19 factorial. These calculations, now this is where fractions absolutely save our lives, because fractions cancel. They are our best friends forever. So I have 28 factorial. Now I have this 9 factorial that I have to break. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, who cares, times 19 factorial, and that's going to cancel. All right, so we cancel that. Now let's cancel everything else that we can. 4 times 5 is 20. Great. 4 times 5 is 20. That's going to kill 20. Maybe I can color code. Let's do that blue. 4 times 5 is 20. Dead. How about orange? 7 times 3 is 21. Great. Dead. Then we can just flat out cancel 2 and 22, get 11 over there. That's better. 6 and 24 here, or purple. 6 and 24, get a 4 there. How about 9 and 27 to give us a 3? And what should I do with 8? I can cancel that 4. Okay, let's see what we have so far. So what survived? 28 times 3 times 26 times 25 times 4 times 23 times 11 divided by just 8. And that's great, right? I can cancel 8 and a 4 and get a 2, and then take this 2 and cancel it with, let's say, 28, get the 14. So all I need to do is just to multiply these numbers straight up. 14 times 3 times 26 times 25 times 23 times 11. We punch this in the calculator and it will give us obviously a large number, but remember that we did not have to go and multiply all the way, right, from 28 to 1 and then keep dividing by these things. We canceled as much as possible and then just got these numbers. So 14 times 3 times 26 times 25 times 23 times 11. $690,690. That's almost 7 million on that binomial coefficient. So to calculate binomial coefficient, now usually in class and what we deal with our applications, guys, we are just dealing with the very basic numbers. If it comes to calculating larger numbers, right, you can just cancel, peel off, so you don't have to calculate everything at once. So you see that, 6 and 2 gave 15, 28 and 29 gave 7 million. So these numbers really grow very quickly. So what we did so far is vocabulary, mechanics, and some prerequisite work. We are not there yet talking about binomial distribution or anything like that. The next concept that we need to cover is called Bernoulli trials. And this is one of the coolest things that I found. Bernoulli trials. Number 1. The experiment two outcomes. And you can call them success and failure. So, success and failure. Labeled as S and F. 2. The trials are independent. Our trials are independent. And then probability of success is probability, is called the success probability, and denoted by P, and it has to remain the same. So, probability of success, not denoted as P, must remain the same from trial to trial. So this is some really cool stuff. Let's take a problem and try to understand. So I'm going to have you take now nuclear physics final exam 10 problems. They're all multiple choice, and you're just going to randomly guess those answers. What is the probability of passing the exam with 70? Right? We're just concerned with passing. We need to explain how these three categories clearly fit in the scenario, because if any of the three fails, it's not a Bernoulli trial, and what we're learning doesn't apply. So we have to be careful about that. So what do we have? We have nuclear physics, final exam, 10 questions, multiple choice, each one has an answer and then 3 decoys, which means four possibilities. Four possibilities per question. Need 70% to pass. No partial credit. Awarded at all for any calculations or anything. So does this fit our situation? Well, the experiment must have exactly 2 outcomes. Each question, in this case, is labeled as a trial, as an experiment. Each question is independent of each other. Your question 2 does not depend on question 1 or question 7, right? So each question is independent of each other, and you guessing B on, let's say, question 1 has nothing to do with you guessing A or C or whatever on a question 2. So we already see that all of the questions are independent of each other, and we already see that with the 4 choices given to you, right, you're either going to guess the right one or you're going to guess the wrong one. So there are 2 outcomes. For each question, there are 2 outcomes. You guessing right or you guessing wrong. You can guess somewhat right. So number 1 is fulfilled because each individual question, which is called a trial in this case, each individual question you can answer right or wrong. So those are the only two outcomes you can have. There's no partial credit possible. So partially right doesn't exist here. You can think about flipping the coin. You can say it's raining or it's not raining. So when the two cases are presented, you are late or you're not late, right? So this is what we have. Two outcomes without possibility of a third one. So one is fulfilled because we can label success as successfully guessing a correct letter, and then failure is choosing one of the other three decoys and having it as a failure, which is a wrong choice. Number two, each question is independent, so none of the questions depend on the previous questions in any way, and you guessing the first exam, second or third, so they're all independent. Probability of success, P, remains the same as you go from question to question. Well, yes, because exactly 1 out of 4 is correct. So what is the probability of success? 25% or 1 in 4. Very good. So right now, I have that the probability of success, that's a lowercase p, is 0.25, and the probability of failure would be 1 minus p, which is 0.75. So you are much more likely to fail than to guess correctly as you are going through this. So this is a Bernoulli trial, and we can now calculate a whole bunch of stuff with this, but we would like to see what is the probability that you are going to pass the test with exactly 70. That means that you have to guess correctly 7 and miss 3, right? For a total of 10, because you answered all the questions. Now, need 70 to pass, but remember, you also pass if you hit 80 or 90 or 100. So there actually should be 4 calculations. One calculation covering 70, one calculating 80, one calculating 90, one calculating 100, guessing all 10. And if you add all of those, because it's OR, right? One or the other, or, so OR is always the addition. We learned that last class, or 2 classes ago. By adding all of those probabilities together, we would have this master probability, right? And you will see what that works out to be. Now, clearly, more questions you have, are you expecting odds to be better or worse? You can calculate that too. Just go ahead, increase questions to 20, and then run the whole calculation again, and you'll be amazed. Now, right now, we understand we understand all of the parts of this problem. We understand how this fits Bernoulli trials, and now we just need to learn the formula that calculates the probability of this discrete random variable, and that would be the major formula that you are memorizing. Well, you need to memorize the other one for coefficients, but so probability that you are going to guess what you need and choose x of probability raised to the n, and then 1 minus probability raised to the n minus x. So this is your success over here, this is your failure, and probability so this is the Boss equation. Binomial probability formula. You are guaranteed a problem on exam 2 or 2 problems on exam 2, and guaranteed at least 1 problem on the final exam to use this formula, as it's very useful thing as we move along. So now I would like to calculate the probability of me passing exam with 70%, exactly 70%. How many questions do I have to answer correctly? 7. So I am looking for probability of x equals 7. Probability x equals 7. So this is n choose x. So I have 10 questions and I need to answer 7 correctly. So this is the way you are denoting that you have 10 questions and you are looking for 7 to be correct. You're not asking, okay, is problem 3 correct? It doesn't matter. Any 7 will do. These are combinations. So any 7 problems from the bunch of 10 will do. I just need 7 to get 70. And now the rest is a probability of success is we can put 1/4 raised to the n, which is oh guys, I have this wrong. Should be 7, not this should be x, not please fix this in a formula. Fix this one. It's not n, it's x. Probability of success. There we go. And now the other one is 3/4, which is a failure, raised to 10 minus 7. Okay, so now I need to go 10 factorial divided by 7 factorial times 10 minus 3 factorial. And then I have 1/4 to the 7 and then 3/4 to the 3. And now we just need to compute this. So 10 factorial is 10 times 9 times 8 times 7 factorial divided by 7 factorial times 3 factorial. And if you know algebra, these calculations here tend to be easier if you use fractions, but you can use your decimals and then just punch everything in the calculator, because we are looking for a three-digit decimal anyway at the end. So I'm just going to simplify these calculations using fractions as much as possible. So now I have, so these cancel, right? And I have 10 times 9 times 8 divided by 3 times 2, that's a 3 factorial, times 3 cubed divided by, and this is now 4 to the 10th power, because 4 times 4, right? You add exponents. So what I have here is 3 will cancel 9, I will get a 3, and 8 will cancel 2, I will have a 4 there. So now I have 10 times 3 times 4 times, and this is 27, divided by 4 to the 10th power. I can cancel the 4 and get a 9th power there. So that's as much as I can. As I said, you can just punch everything in the calculator right away and get the answers. So what I have here is 30 times 27. 30 times 27 divided by 4 raised to the 9th power. The answer is 0.003. Your chance of guessing randomly 7 out of 10 correctly is 0.3%. If you have four possible answers. Yes, for each question. That's the formula for binomial coefficients.
It's supposed to be 10 minus 7. I mean, the equation before is
Yes. I was probably calculating ahead. Instead of calculating, I talk too much. That's a 7.
You have it correct.
Oh, I have it correct on the bottom. Okay, good. Whew. So it was just wrong in the formula. I have it correctly as a 3 factorial down there. Good. All right. So do you see what the probability is that you are going to guess without studying? You take a 3-year-old to randomly circle your Statistics1 multiple choice 10 exams. That's the probability that you are going to, or that 3-year-old is going to pass the exam. Is less than 0.5%, right? Now, clearly, to get 8 questions correctly is even worse. To get so why is the lottery thriving? Why is the lottery thriving? Right? You are more likely to be hit by lightning twice in the same day than to win a lottery of any kind. That's really interesting. Let's take a look at one of those lottery. The pick 4, right? Is the one of them. So we have 4 digits that need to come up. And if they come up, you win. So, but they have to match whatever is on the computer, right? So, what is the probability that you're going to hit one of the digits? Well, it's 1/10 on each one, right? Because they're all independent. So, the odds of winning are 1 in 10,000. Even if you went and you bought 10,000 tickets, some of them might repeat. You're not even guaranteed to win, even if you invest $10,000, right? Plus, you can't physically buy 10,000 tickets in a day because it's a daily thing. They know what they're doing at all times. They make a lot of money. Let's see another example other than guessing on the exam. After this, we have to figure out the mean and median. So this was pick 4. We did not use binomial on this. We just used the basic counting for each one. Let's find the word problem in here. Traffic fatalities and intoxication. Sounds right down the alley for the book. 579 on the homework. The National Safety Council publishes information about automobile accidents in Accident Facts. According to the document, the probability is 40% that the traffic fatality will involve an intoxicated or alcohol-impaired driver or non-occupant. In 8 traffic fatalities, find the probability that the number y that involved the intoxicated or alcohol-impaired, okay, is exactly 3, at least 3, or at most 3. Okay, so what do we have? You will have to disconnect the mathematical terminology from your personal beliefs or whatever. When I say probability of success over here, that means we found the intoxicated person, because it is 40% chance that whoever caused the accident is intoxicated. Once we examine the accident, if we find that the person is intoxicated, we successfully determine that the person, that the fatality, that the accident and therefore fatalities were caused by intoxicated person. So I'm not saying it's success to be drunk and drive. I'm saying it's successful to determine that the person, right? So be careful about that. Probability of success is 40%. Clearly, immediately, probability of failure is 60%. They are looking for, they're looking into 8 accidents. So n equals 8. And let's say they want exactly 3. So what are the probability that exactly 3 out of 8 accidents were caused by intoxicated person? So what do we have? Well, we're looking for probability x equals 3.
Sorry, what was 3 again?
3 is, the question is 3. The question states, in 8 traffic fatalities, find the probability that the number that involve an intoxicated or alcohol impaired driver is exactly 3. So 3 and 8, right? So we have 8 choose 3. Then we have our 0.4 to the 3, and then 0.6 to the 5. That 5 is 8 minus 3. So now, this is 8 factorial divided by 3 factorial times 8 minus 3 factorial. I'll do it right this time. And then we have our 0.4 cubed and 0.6. You know what? Instead of writing 5, I'm just going to put 8 minus 3 over here, and then in the next step is 5. So now, I'll expand the 8 factorial, 8 times 7 times 6 times 5 factorial. I have 3 times 2 times 5 factorial. And then I have 0.4 cubed and 0.6 raised to the 5th power. 5 factorial cancels 5 factorial. 6 cancels 2 times 3. So all I have to worry about is 8 times 7 is 56 times 0.4 cubed times 0.6 to the 5th power. So that's 56 times 0.4 raised to the 3 times 0.6 raised to the 5. And the probability is 0.27279. So about 28% chance that in 8 deadly accidents, 3 were caused by a person under the influence of some kind, whether it's drugs or alcohol or whatever, right? So that's 28%. By the way, autonomous driving eliminates all of that. If you can find your cell phone, you're going to take it home. Just need to push one button. Take me home. Over 30,000 die every year in the United States alone in car accidents. 30,000. And then I remember last year there was one person who died due to autonomous driving, and everyone said, like 1. 30,000. Yeah, I'll take those odds. You take me anywhere. I don't want to touch. I don't want a car with a steering wheel at all. With those odds, just walk in with the entire front windshield being just a widescreen TV. Right? That's the car I want. I'm serious. 30,000 dead, 1. the news were like, oh, but the software didn't see the back of the trailer that was against the sky. It looked the same, so the computer didn't stop. And this guy drove right into the truck. The car actually drove right into the truck. And I said, yeah, it was Tesla.
Yeah, I know. It was called that one time.
I know, it was one. And I said, great. I mean, yeah, this guy died. That sucks for him, but won 30,000. Like,
the driver is capable of this. If they see it, if he's grabbing.
yeah, but wasn't paying attention. So yeah, but as I said, even in that case, right? Even in that case, I want the car that I can't see out of it. I just, I want the screen that goes around me like this, and a rotational chair in the middle of the car, and I can just like rotate and watch like 4 movies at the same time. How about that?
This is virtual reality.
Yeah, I know, but it's anything. So, so now we see, right, 28% chance that all of those 8 fatal accidents were. Now, the other questions are more interesting. There's another wording, the other part of the question, that says at least 3, and then at most 3. Now, that involves calculating other probabilities from scratch. Remember, for your exam, to pass exam, you need at least 70. 80 is okay, 90 is okay, 100 is okay. So when I say you pass the test at least 70, you immediately, that at least, you know that anything bigger than that is also fine. So what is the probability that at least 3 were intoxicated, right? At least 3 means, well, could be 4, could be 5, could be 6, could be 7, could be 8. And now we have to repeat this calculation for each one of them and add them, because it's or, right? At most 3. Well, none of them were, or 1 or 2, right? At most 3, not more than 3. So just be careful with the wording and use the same logic that you would use when you talk to your friend, right? Well, at most 3 of us will go to the party, right? At most 3 of us, or at least 3 of us, right? You have the notion of that in your head. So transfer that knowledge, right, into this, because it's the same thing. And then you will know whether you're supposed to calculate the ones below or ones above, and you will add them all together to come up with the overall probability. We can also get the language, how about, between 3 and 5? Well, between 3 and 5, that's 4, right? And then you have 3, 4, 5. So you add them. Px equals 3 is exactly 3 out of 8 were intoxicated. At most 3. So I'm just going to now put these other questions here. So when we are talking about wording and notation, Px equals 3 is exactly 3. Exactly 3 out of 8 are intoxicated. Px larger than 3, Px less than 3 with the equal signs. So what is this one? Is it at least or at most? At least 3. At least 3. Now guys, that's going to be P of x equals 3 plus P of x equals 4 plus ... P of x equals 8. You have to add them all. So you'll have a lot of annoying calculations there. At most 3. Which is in this case Px equals 0 for none of them, plus Px equals 1 plus Px equals 2 plus px equals 3. At most. Well, you have out of 8, right? So you have the cap always, right? We had the 10 questions on the exam, so right. So for your exam, at least 7 questions, and if I say at least 7 questions, that means 7, 8, 9, and 10 is for passing, right? At least 7 questions correctly, but 8 is okay, 9 is even better, and 10 is perfect, especially for nuclear physics exam, right? I mean, you want to hire someone who has like A across the board, right? Do you really get someone over there working as a physicist in a nuclear plant with, you know, C's across the board? Just one push of a button away from nuclear disaster. Like Homer Simpson. There we go. Now I see who watches. Good. Let's see if we can find something else that is interesting. Oh, come on. This is too good to pass on. Love stinks. 581. The article Love Stinks in American Demographics reports that Americans split their significant other for many reasons, including indecision, infidelity, and simply growing apart. According to the article, 35% of American adults have experienced a breakup at least once during the last 10 years. Of 9 randomly selected American adults, find the probability exactly 5, at most 5, at least 5. According to the article, 35% of American adults have experienced a breakup. By the way the problem looks at this, a breakup is a success because they're looking for a breakup. In your personal life, you would probably label breakup as a failure, right? But from the point of view of the problem, when you get what you're looking for, it's labeled a success. It doesn't matter whether it's death or breakup or whatever, it's labeled as insurance companies, when they do the probability of how probable is to, right, and then they figure out the premiums and so on. What is the probability that someone, right, is going to, or health insurance, life insurance benefits and so on. Finding a case where someone died is labeled as success, even though it's bad for both parties, right? They have to pay out, and the person is dead, right? So it's a lose-lose combination. But for calculations, for purposes of calculation, it's labeled as success. So in this case now, when we are talking about this love problem, 581, probability of success is 0.35%. Therefore, failure is 0.65%. And they say out of 10 random, 9. So out of 9 people, they're asking for 5, and then at most 5, at least 5. So probability of exactly 5 people having a breakup is 9 choose 5, and then we have our 0.35 to the 5 and 0.65 to the 9 minus 5, which would be 4 in the next line. So now I have 9 factorial divided by 5 factorial, 9 minus 5 factorial, 0.35 to the 5, 0.65 to the 4. And now we calculate. So this is 9 times 8 times 7 times 6 times 5 factorial divided by 4 times 3 times 2, 0.35 to the 5, 0.65 to the 4. These 5s are gone, and then I have my 6 times, 6 and this one, and then I have the 8 and a 4. That gets me a 2 over there. And I just need to punch all of this in the calculator. I have 18 times 7 times 0.35 raised to the 5 times 0.65 raised to the 4th, 0. Right, so it's about 12% chance. Exactly 5. And then we have at least 5 and at most 5. Where's the problem? Between 6 and 8 inclusive. That's a good one. Between 6 and 8 inclusive, which would be probability x equals 6 plus probability x equals 7 plus probability x equals 8. You calculate. So each one of these is individual calculation of this. And then you get those 3 numbers. So you have to do 3 of these calculations. And you get the values. And you just add those numbers at the end. So this one would be 9 choose 6 times 0.35 to the 6, 0.65 to the 3, plus the next one is 9 choose 7, 0.35 to the 7, 0.65 squared, and finally the last one plus 9 choose 8, 0.35 to the 8 times 0.65 to the 1. And then each one of those provides you with a number. You will just add them all, and that will be the answer. So all of these problems, you have to look for what we would say binary, right? You are looking for 2 possible outcomes, heads and tails, true or false, success, failure, right? Guessed correctly, guessed wrong. Male and female, since this is statistics class, like in liberal arts they have more choices. I'm serious. It's getting ridiculous out there. So we have the rules over here, and if you follow these rules, none of the stuff with the replacement, right? Without replacement, all those things. Independent trials. Your question 1 on a test has nothing to do with the question 2. Your accident number 1 doesn't have anything to do with accident number 2. They might not be even in the same states. I don't mean your particular accident, the accident that you are investigating as a, right? So any of the problems we did, right? Each trial is independent from other trials. At the end, we have 2 more formulas, which are very simple. Mean and standard deviation of binomial random variable, and these are a joke. So mean and standard deviation of a binomial random variable the mean mu is simply n times p. P is the probability of success. N is the number of everything, right? We had 10 questions on the exam. We had 8 accidents that we looked at. We had 9 Americans that we looked for breakups, right? So that's n. And this is your probability of success. So you just multiply those two numbers and you have the mean. Mean is also known as expected value. And then we have a standard deviation. You know it always involves the square root. So you start with the np times 1 minus p. So it's the number of cases you are examining times probability of success times the probability of failure and the square root of that. Extremely simple formulas. No charts, tables, or any of those calculations that took you 7 years to do. This is just multiply 2 numbers and multiply 3 numbers to say. So let's calculate the mean and standard deviation for those exams that we had. So we said 10 exams, probability of success was 25%, right? Because to guess correctly, it's 1 out of 4, and the other 3 decoys are all wrong. Which will mean that 1 minus p, which is probability of failure, is 0.75. And you have 10, so not 10 exams, 10 questions. 10 questions on the exam. So the mean is 10 times 0.25, which is equal to 2.5 questions. That's the mean. Nice, right? And that's the mean of what you should get correctly. Expected value, 25%. And then you have the standard deviation of square root of 10 times 0.25 times 0.75. So let's see what we get there. Square root of 0.75. 1.37. So technically, not even in your wildest dreams, you should be able to score 50 on this exam. Right? You'll be in less than 2 standard deviation, which means that less than 1% of students would manage a 50. Less than. Obviously, you have to have a lot of those students take. So very simple formulas. You just multiply 2 or 3 numbers together, and you have the answer. We are done with chapter 5. Next class and the next week, so the next 3 classes, we will finish chapter 6. And that will be it for next exam. So we will talk about it next week. So 6.1 and 6.2 on Thursday. On Wednesday. Yes, on Wednesday. I can't get used to these Monday, Wednesday classes. I've been teaching on for 10 years. They're so elusive. Bye.